All right, so so here we go. Oh, that I'm still building that. That one's being okay. You can see when it's loading. I sit here and watch it sometimes, and then I'm like, it works much better if I don't even watch it. You know, but if I sit there and watch it, it drives me nuts. All right, here's another mass spectrometer problem. Except again, we've got to go back to chapter 19 stuff. Okay, when we bring this in, we're going to look at, we've got to look at chapter 19 things and what's going on here. All right, so okay, so we got the mass. We know the charge. Here's the charge. Here's the mass. So we've got F equals QVB. So we just start there. We'd kind of go, okay, well, F equals QVB. That's fine. Now let's read it. It is accelerated through a potential difference of 1.2 times 10 to the 6 volts. Okay? And it's got an energy, and it's got a charge of 2e. Okay? So actually the energy of this thing, we could say the energy of this thing is 2.4 is 24 is 2.4 mega electron volts. That's the energy. But what do we remember? It's going through that huge, and it enters it back. So we've got the magnetic field. We know the charge. I need to find the force. What is the speed? Oh, I need to find the speed before I can find the force. Hey, if it's accelerated through something, do you remember Q times V is equal to 1/2 mv squared? Remember? Aha! You set that up, you're golden. Okay, and I'm going to bring these notes with me to class. I need you to bring these problems with you to class so we can get them. All right, now we need to learn a new concept real quick. Done the mass spectrometer, kind of beat it to death. And then we can find the radius too, because once again, when we find the radius, chapter 19 is the QV is equal to 1/2 mv squared. That's what we learned from chapter 19. It's equal to the kinetic energy because it's giving up that potential to be shot through there. Okay? Very fun. Good stuff. All right, now let's learn. Now, okay, so if a charge is moving, what happens if we have a wire? Well, it's got charge moving, right? So it's the same thing. It's like the half-price store. It's the same thing. Okay? It's the exact same thing when I've got a current going through a wire. And it's going through a perpendicular force. Like that. Okay? Same thing. In this case, the force is going, the wire's going this. So we'd have a force on this wire coming at us out of the page. Here's the force. Let's do it this way, where we've got a magnetic field that looks like this. And we've got a wire with the current coming at us. This means I is coming at us. Okay? So here, I'll get my big ass thumb my thumb down there. Magnetic field's going in the direction of my fingers. Boom. We're going to treat the current like a proton again. And it works. I mean, that's the force it would feel. It's going this way. And so this would feel a big force going like this. If I had a wire that's like this, with the current going this way, and let's put a magnetic field going like this. Here's my B field that's hitting it. Boom. B field going into the page, finger going that way, force going straight, going up. There's my force. You're going to do that 3 times with this guy. Oh, but I didn't tell you how to do the force. Here's what happens. We basically derive this F equals QVB. Whoops, got to be careful. F equals QVB. We basically take this guy. Remember, if we take Q over T, I get I. Okay, times VB. Well, that doesn't help. But look what happens if I take Q over V What's V divided by T? Well, that's how long it takes to go from here to here. That's that distance. V over T is equal to the distance that it took the length of that wire. Cool beans. So I say this. Oh, wait. V times T, that was bad. V times T is equal to the length of the wire. Okay? So if I take Q over T times V times T times B, I get a force. And then notice the T's cancel. Well, what's Q over T? That's I. What's V times T? That's L. That's B is equal to 4. Maybe I should stick with the slides a little bit. Oh, well, here's what we're talking about in a wire. Okay? The magnetic force on a moving charge pushes the wire to the right. Okay? B field's going down, current's going this way. Boom, it's going to get pushed to the right like this. In fact, they've got a little video I could show you on it. It's kind of nice, but just trust me. I mean, this has been done a million times, so they got it. So this is what I just showed you. F equals ILB, sine theta. Again, it's the same thing as QVB, and I like to keep everything 90 degrees. So let's go ahead. So that's the way you do this problem. Right here, when you bring this one in, when we start with this one, we go, oh, okay. Well, now what might be tricky for you is this B field that's going straight up. It's going straight up all over the place. The B field is going up here. It's 90 degrees with this one. It's 90 degrees with oh wait, it's perpendicular with this one. What would that one be? You are so right. Zippity doo-dah. Okay. So let's take a look at this one, and then we'll stop this nonsense. I'm going to keep these with. No, I'm going to put these. I'll put those in there. Yeah, I got to put those as part of the notes. Where's my other notes? Don't I have any other notes? Did I throw them away? Oh, that would suck. No, here they are. Just look at them. Yeah. Does Rex know what he's doing? No. Does he ever? No. Is he really that big of an idiot? Yeah. Does he work at it? Yeah. All right. Anyway. Okay, here we go. The voice coil of a speaker. Notice magnetic field going in. It's because we flipped the poles here. So the force, boom, 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 boom. Push that. The voice coil has a diameter of 0.0025 meters and contains 50 turns of wire and is placed in a 0.1. That's a pretty big magnetic field. The current in the voice coil is 2 amps. That's a big current too. Determine the magnetic force that acts on the coil and the cone. Okay, the coil and the cone. All right, cool. There you go. It's 50 turns. So it's got this diameter. We've got to find out its length. That's the tricky part of this. 55 turns with this much diameter. Okay. Determine, and the voice coil and cone have a combined mass of 0.2. Find their acceleration. Okay, so once we find the force, we divide by the mass. But the tricky part of this problem, they think they're so slick. And so we should probably get used to this. They're saying the diameter was equal to 0.0025 meters. Okay, well, the circumference is equal to d 2 pi r, right? 2r times pi, so pi d. That's the circumference. All right, well, they've got, so how much wire is needed? Well, they've got that times 55. So the length of my wire is 55 times pi d. That's all they're saying. And then the force becomes ILB. That's it. That's all they're doing there. No biggie. They made it sound hard. There we go. And it's perpendicular to the magnetic field, so we're all good. 0.86 newtons, 43 meters per second squared. That's a lot of acceleration. That's really booming back and forth. Okay. Now this is one of those things where they've got, as you move through the sea, as the moving seawater goes through here, we create through these two electrodes, all right, and creates a huge we got a huge magnetic field that's pointing up here. Seawater goes through there, creates a huge force going this way, which will push the boat this way. All right, because it creates a tremendous amount of force. Electric field going like this, B field going up, boom. Inside the ship, they've got this huge magnet that runs there. Maglev trains kind of work the same way. All right, so let's stop here, and then we'll do the torque in a loop, because we got some problems on torque. We're going to get torqued off. As a matter of fact, looky here. And it's not that hard. NIB, man. That's the torque. Remember what torque? Force times lever arm. So if we put something inside a magnetic field, if we put a current inside a magnetic field, it's going to start spinning. That's what I was looking at, that one parallel plate capacitor that we had. Started spinning. All right, cool. Let's stop here. This is probably way too long. Oh.